Okay, welcome back to Scientific Computation using Python. In this lecture, I would like to go over the airfoil code and factor it out. Factoring out as code means writing it using functions to make it more easy to read and also more modular. So this code is reading an airfoil, finding its panel centers and panel normals, and then using curve plots draws the, the panel normals starting from the panel centers. Everything starts with the reading of the airfoil file. Once that is done, we have foil X and foil Y coordinates. Using those coordinates, we get the panel centers. Also, using the foil coordinates, we can get the tangents and then the normal vectors. So let me factor this code a little bit to make it more readable and more modular, as I said a while ago. So these two are really global variables, so there is no point of putting them into functions. But here I can define a function. Let's call it getFoil, and then I can give it a foil number. Let's say n is equal to 0, and then so all this code here I can use tab to put it in the function. So this is what the function looks like now. Okay, I would like to get a foil. Which foil? The first one in this list, the directory. So file name would be, of course, I should now be using n here, because if n is a different number, the file name should be accordingly changed with that. And after this line over there, I have my foil X and foil Y coordinates already. So I can return foil X and foil Y. So this function will get the coordinates of a foil, of this given foil. What I also want to do in this function is to draw the foil. So I would like to put the plot functions in there as well. So in this case, I am getting a foil. This function is returning the xy coordinates, but also the function will plot. The function will plot the foil. Okay, so the rest of the code at this point, I am not going to use them. So let's comment them out here. Okay, so this is the only code that I have. Now running it will define the function, and calling the function, for example, xy get foil. If I don't provide a parameter, it will automatically be 0. So let's see that. And then that foil will be drawn in here. Therefore, when I say get foil, it will get the coordinates and draw the foil automatically. So let me run that. Okay, so I have my foil loaded and the coordinates are in x and y. This is x and that is y. Okay, that's next. I would like to improve this function a little bit by providing a parameter draw foil, and I would make it false as default, and then I would draw the foil only if the draw foil parameter is true. So this is, then I should write if draw foil. If draw foil is true, then all these things will execute. Otherwise, it will just return the foil X and foil Y. So if I run this again, by default, this zeroth airfoil is loaded, and by default draw foil is false, so this part didn't execute. So let me show you this how the parameters work. So if I say 0, exactly the same thing would happen. If I use a different foil, that will load its x and y values, and I can see those x and y here, x and y. This is different to the previous one. Now if I want to see the foil drawn on the screen as I load it, then I must use draw foil parameter as true. Now getFoil function has two keyword arguments. N is the order of the foil, and draw foil shows if it should be drawn after loading. So if I set this true, it will be loaded and drawn. So this is my second airfoil, and because I said draw foil true, it draws as well. So how about the third one? Okay, yet another foil. Also have a look at these points here. The sampling is quite a lot on the leading edge over there. When we do the panels, you will be able to appreciate the large number of foil points there. Okay, so far so good. So next I want to do another function, get get panel centers. Get panel centers. Okay. Now if I input the foil coordinates x and y, it should give me the panel centers. How do I do that? These two lines that we wrote before calculates the centers. But of course, the parameters x and y here should be used inside the functions foil, or I can call it with foil x and foil y. That would be easier for this case. So this function returns the center coordinates. Okay, get panel centers. I can call this function xc, yc, get panel centers, and I should be inputting x and y, these two values that I loaded. So if I supply the xy coordinates, it will get me the centers using these two functions. Be careful here, I am writing x and y here. So x and y will be passed to foil x, foil y. This should be calculated and returned as xc, yc. Okay. But if you want to see the center coordinates, x center, y center, and then let's make it a little larger, so we will see it on top of the same figure. Okay, so here are the center panel centers. As I said, there are a large number of panels over here. So if I want to do this for my first airfoil, here are my panel centers. We are almost done. The last function I want to do is get panel normals. Again, my input will be foil x and foil y coordinates. So here is the function that we used the last time. So up until here, let's go over this once more. Okay. Take the commenting out and push this using tab. So let's have a look at this function. Let's remember how it works. So if you supply foil x and foil y, it calculates a tangent x and tangent y and calculates its length of that vectors, and then this normalize those vectors. That is the tangent vectors of the panels, and the normal vectors would be the order reversed and with a minus. If you multiply this to the scalar product is 0, showing that they are perpendicular. So I should return the normal vectors. Okay, good. So I defined 3 functions, and now I can work with my airfoils quite easily now. I say get foil, draw the foil, so I get the coordinates, the centers, and the normal points get panel normals. And the input parameters are x and y coordinates of the foil. These are the xy coordinates that I used here. Okay, I showed you that. Let me run this. Okay, so these are the x and y arrays here. X and y arrays. X center, y center. And then the x component and y component of the normals are these. And of course they are normalized. So let's plot the curve plot to see that everything is works as expected. So curve plot at the centers. What do I want to plot? The normal vectors using a scale like 10 should be okay. Remember, after the scale parameters we have the alpha. 0.4 is transparent, quite a transparent arrow. So let's have a look. Okay, so my airfoil, center points, and the normals. It works beautifully here. Let me do for another airfoil. So, and when I say N1 here, X, Y, centers, normals, everything will be calculated for the next airfoil. This is, remember, 2032C. The next one is a different one. So this is A18. As you can see, the foil is different, but the centers and the normals are calculated accordingly. And this fifth one, what do we see here? This is an airfoil with a large number of panels, and I can see that, for example, how many panels are there. So these are the centers of the panels, and then len xc will give you. So this airfoil has 179 center points, therefore 179 panels. So large number of panels compared to the other one, which has about 35 panels. Good. Now when I said factoring out, this is what I meant. So basically I have put my program in functions so that I can load my airfoils directly using this function. So the rest of this program here on the top, I am not really concerned about them anymore. So when I say get foil, it gives me xy coordinates. Then I say get panel centers, supplying x and y, gives me the centers. Panel normals gives me the normal vectors. So usually this is where the computation starts. Now I would like to show you something on top of what we learned until here. Okay, let's clear this and go back to the original airfoil and let me put it again. Okay, now to make you understand how this works a little more, let me do the alpha even more transparent. So these are my transparent normals. What if you want to see just only one of them? For example, the 25th one. In that case, uh, so this will draw the 25th panel normal once more after it is drawn everything again. So this is the coordinate where it is drawn. So I am pulling the 25th element from the x center and y center coordinates, and for the normal x and y vectors likewise. So I am pulling the 25th element and will draw that again here. So this time I want to use alpha 1 so that you can see it clearly. Okay, let's run this. Okay, so all my normal vectors, and this is the 25th drawn uh, specifically. So how about the fifth one? So this one is the fifth one. So I can draw these normals independent of the others. If I comment this part out, it will just draw that specific vector. And if you want to see that vector, x center 5 and y center 5 should give you the coordinates. The y coordinate and the x coordinate. Sorry, these are I'm sorry, these are the coordinates of the panel center. The components of the vector should be nx5 and nx and y5. So as you see, the y component is larger compared to the x component, showing that this vector is more aligned towards the y axis. Okay, good. This part I don't really need, so I want to take that, comment that out, and then bring the vectors back. Okay. Now, next I would like to do a free flow in the x direction. I want to define a free flow in the x direction. So let me first draw the flow so we know what we are talking about. I want to use stream plot, therefore I want to define a mesh grid for that. So I want to take this here. Okay, so this creates my mesh grid defined. Now I can create the components of my free flow in the x and y directions. For the x component of my velocity ux, I want to do ones like the x array, and for the y components I don't have a y velocity, so I want to do the zeros like x. I can do this y or x because they are the same shape. That wouldn't make a difference. Okay, so in other words, this is the free flow that I was talking about. So maybe I should comment here free flow. So this free flow is 1, 0 free flow. Okay. On top of the airfoil, let's plot this and see what the free flow looks like. Okay, that's my airfoil, and this is the free flow. You can see the arrows here in the x direction. Okay, if you want to play with this a little bit, how about we make this flow in the northeast east direction like that. So let me run this. There, now this flow goes 45 degrees with the horizontal. Okay, that looks good. I want to return back to my horizontal flow, zeros. And then the figure is a little bit cluttered, so I want to get rid of the panel center points where I draw them here. So I want to take that off, or maybe even better, I can comment that out. So let's run it. There is the horizontal flow with the airfoil. The airfoil points are also shown. I can turn them off if I want to. That's in the function here. So here is, by taking that off, I can remove the foil points as well. Maybe this is even better. Okay, now let's do something meaningful after this. I want to do I want to ask a question like this. This free flow intersect with each of the panels. Uh, can I calculate the component of the free flow when it hits the panels along the panel normal direction? In other words, what is the flow's projection on the panel normals? To answer, it's not very difficult to answer this question. To do that, I want to take this away. I am not going to draw the stream plots. The reason is to show you, to highlight that it is not about stream plots. I can do it with curve plots, and it will be easier to do with curve plots. So let's go back to our original. So now, what if I have a free flow in the x direction and I want to find the projection of it along the normal vectors of two panels? So this is how we do that. I actually discussed this in the previous videos, how to do a projection of a vector on another. So I am following the same formulation. So I do the projection, I calculate the projection magnitudes by this, and so this is the normal vector times the free flow in the x direction plus normal vector in the y times the free flow in the y direction. So this is the projection intensity. Now after this I can again do the curve plot in the same way. So I want to do it on the centers and the vectors, but these vectors must be scaled with the projection. Projection times nx, projection times ny. The previous video explained how I come to this notation. So if you are not feeling comfortable with what I am doing here, study how we calculate the projection of one vector and over another. In this formulation, I am doing the, let me write that here, projection of ux, uy vector, which is the free flow vector, along the normal nx and y vector. Okay, so ux and uy, and I must define the free flow here. Ux, uy is going to be 1.0 and 0. So I have a free flow in the x direction. I do the projection over the normals, and then I do the curve plot of that projection. So let's have a look what this looks like. Okay, I already have something in front of me. First, let's do the normal vectors very transparent so they don't clutter. So the normal vectors are transparent. And then the projection vectors, let's highlight them by making them, for example, 0.75 uh, 0.75 opaque, and let's run this. Okay, let's try to interpret what we see. So when you have a free flow in the x direction, you see that, for example, at this point, the projection of a horizontal vector on a nearly normal vector is almost zero. So we don't really see them here. But when the foil normals are more aligned towards the x-axis, we begin to see the projection vector. Something more I can say about this figure is basically these are the parts where the lift is created, or even better, the dynamic pressure is highest at these points, because at these points the free flow is really hitting the airfoil surfaces. To make it, I can make the scale 5 to make it them even larger. See, basically the horizontal flow comes this way, and the projection vector is in the opposite direction actually, with respect to the panel normals. I have components over there as well with the flow. So a flow velocity creates projection vectors on the normals. Now, in the next part, I want to introduce vortices and do the same operation with vortices. In other words, I want to create a flow with vortices and then find the velocity projections along the normals due to those vortices in the next part. Okay.